Now for a look at some rational functions here. So a rational function, you may see the word ratio in there. Yes, ratios are fractions, but I don't want you to just think that when you see a fraction, you have a rational function, because if I gave you f of x equals 3x over 2, well, that's really just a polynomial because it's 3 halves times x. All right, and you can plug in any x value and get any answer there. That's not a rational function. What makes a rational, well, here, let's do it over here. What makes a function a rational function is you have a polynomial in the numerator and a polynomial in the denominator. Okay, so you have two different polys here. And what that leads to are things that might make your fraction undefined. And that's where weird things happen, like vertical asymptotes and holes. There is nothing we can cancel out. I can't take anything out of 2x minus 3, so that's simplified. There's no factor. And x plus 6 is simple. That's a simple factor. There's nothing else to take out. So if you can't cancel out your issue downstairs, what happens is you're going to have a vertical asymptote. What makes your fraction undefined and you can't remove that issue? Well, you're going to have a vertical asymptote at x equals negative 6. We did that last year. And if you didn't, there's how you do it. All right, there's our vertical asymptote. I should continue that. There you go. And so with rational functions, what we want to do is we want to evaluate the limit where the function is undefined, because there might be an issue there. That's our concern. So let's see what happens. Does the limit as x is approaching negative 6 of our function is 2x minus 3 over x plus 6, does that exist? Okay. For this to exist, we must see what's happening on the left side of negative 6 and the right side of negative 6. I put the question mark right there because we're not sure if they equal each other. Let's evaluate. Up to this point, we've been plugging in our x values and getting answers, but notice now what happens on both sides. If you just plug in your negative 6, well, we're going to have undefined issues. Okay, so this gives us a problem. So how can we evaluate this? Obviously, I have the graph right in front of us there, but if you didn't have the graph, how could you evaluate this? Well, notice here, you are coming in from negative 6 on the right side. Let's look over here. This would be negative 6 on the left side, and let's do it in a different color so we can see this would be coming in on the right side. So let's pick an x value on either side. We could do a test point. All right, so for the left, well, if that's negative 6, the left, how about we do something like negative 6.0001? That's definitely on the left. And what if we were to take a test point on the right of negative 6? We could do something like negative 5.9999 or something really close on that side. And what happens is when you take those test points, you can do that on your calculator, is, well, if you plug in that negative 6.0001, what's going to happen is you're going to get yourself a very large y value. It's shooting up towards positive infinity. And the opposite holds true when you plug in that other value here, negative 5.9999. What's going to happen is you're going to get yourself a very large number with a negative in front. So since these two are not going towards the same place, they are going different infinities, the limit does not exist. Let's notice what happens on this one now. If you were to just do what we did before, take your value and plug it in, well, now here you're going to actually get something different. Instead of having a number over 0, here we get, let me write it here. You're going to get something, you're going to get 0 over 0. 0 over 0 is a little bit different than a number over 0, because a number over 0 is undefined. That's going to infinity or negative infinity, but This is called an indeterminate form. And we simply can't, form. We can't determine if it's 0 or infinity. You plug it in, you get a 0 in the numerator. Well, remember, 0 in the numerator, that's supposed to mean it equals 0. But 0 in the denominator, that means it's undefined. You can't divide by 0. So here's what we do. The next plan of attack when that happens is try to factor. Okay, so here's what we're going to do. We're going to factor this one and see what happens. The limit, as x is approaching 0, the numerator has a common factor. And if you take out that common factor, you get that. The denominator also has a common factor. And once you factor, then and only then can you start canceling out common factors. I have an x with an x. X over x is 1. They cancel out. They're multiplying. We can cancel them out. So that's going to leave us with something that looks like this. X minus 2 over x squared plus 7. Well, we just factored our problem out. Let's give it a shot. Let's see what happens now. So go ahead and plug in your 0 and your 0. And when you're evaluating it, that's what we're doing right now. We're plugging in a 0. That's when you're dropping the limit. If you haven't figured this out by now, we have a limit question, but once I evaluate it, once I take that x value and plug it in, we're evaluating it. That's when you get rid of the limit sign, this thing. Negative 2 over 7, there's our answer. The limit, as x keeps getting closer to 0, it's approaching y equals negative 2/7. Do you remember this? When you can take out a common factor, now here, if I were to have an x equals 0, normally that would be an issue. That would give me a 0 times something would be undefined, but we're able to cancel that issue out, okay? So if you can cancel that issue out from the denominator, if you can remove it, that's when there's going to be a hole in your graph. You might remember that from last year. Okay. So with an asymptote, it's when you cannot get rid of your problem downstairs. And when you have a hole, it's because you can cancel out that problem downstairs. This is what the function looks like. And if you notice, right here, there's a hole when x equals 0. Okay. But aside from that, it's approaching y equals negative 2/7. This number right here. And this y value right here is negative 2/7. The limit is approaching negative 2/7 as x is approaching 0. Here's another one, and if you notice when you first plan of attack, try to substitute, do a direct substitution, see what happens. But here you'll see that you're going to get 9 minus 9, which is 0. When you get here, you get 3 minus 3 is a 0. When you get that 0 over 0, that indeterminate form, that means you must do something to help yourself. The next plan of attack, like we talked about, is factoring. So let's see if we can factor this. We have the limit as x is approaching 3. Now the numerator is the difference of two perfect squares. You might remember that. I hope you do. When you do that, you don't need to put that in parentheses, but that is one simple factor right there. And what we get to do is we get to cancel common factors. Okay. What are you left with? Well, now you are simply left with this, right? Mathematically, all we did was cancel a common factor out. We're allowed to do that. Now we can evaluate it. Remember, when you evaluate it, that's when you drop the limit piece and you plug in your x value. So it would be 3 plus 3, and that would give you 6. The limit as x is approaching 3 is 6. Now those last couple that we just took a look at, they were factoring from methods we've learned in algebra, but sometimes you're going to get something that you're not 100% sure what to do. Let me make all this smaller. Let's take a look at this one now. And I'm going to put that over there. I want to put this up here because there are going to be some of you who want to memorize this and get to know it. It's not that hard to memorize, but if and when you come across the difference, the sum or difference of two perfect cubes and you're trying to factor them, this right here is the plan of attack, okay? So if you did want, you could technically factor this out because this is a cube. This is x times x times x, and this is a cube. This is 2 times 2 times 2. So this is, you can factor this. And then what will happen is the x minus 2's would cancel, and it's a fairly straightforward question, but many folks don't remember that. They won't remember how to factor the difference of two perfect cubes or the sum of two cubes. Here's another plan of attack. You have yourself a fraction. Don't forget, a fraction is nothing more than division, right? If I were to do this long division, I could take the denominator and put that on the outside, and then I have the numerator, and you put that in the inside. But with polynomials, you need to remember to put placeholders. You don't have an x squared, and you don't have an x, so those are your placeholders right there. If you want to see it done long division-wise, I'll do that in class, just ask, but I'm going to focus on synthetic division right now. With synthetic division, you don't put the factor. What you do is you set it equal to 0, and you're going to get x equals 2, so what you're going to do is you're going to divide by 2. And then what we're interested in is we're interested in these coefficients. I have a 1, 0, 0, negative 8. Here's what we do. We bring down the first term. We multiply these two, and you get 2. The product goes there, and you add up the column. You repeat the process. You take these two numbers, and you multiply them. 2 times 2 is going to give you 4. You put the product there, and you add the columns. Multiply 4 times 2, and you're going to get 8. And when you add this column up, you get a 0, and this last column is the remainder. This factored nicely. There's no remainder. This is your constant. This is the x term, and this is the coefficient for the x squared term. So when you divide this, you get the same thing as this. X squared plus 2x plus 4, and we can continue. Let's evaluate. Remember, when you evaluate is when you can drop this limit, and I'm going to plug in a 2. Everywhere I see an x. So that means I have a 2 here and a 2 here, and that's going to give us an answer of 4 plus 4 plus 4, which equals 12. So here's one where we can't take out a common factor. We can't factor it out. And synthetically dividing, well, you're going to have there's a radical in there. Well, here's my suggestion. The next plan of attack. When you have a radical in your limit, or at least at this level in math, we are going to be multiplying by the conjugate. If you don't remember what a conjugate is, if I give you something like this, x minus 2, the conjugate of that would be x plus 2. All right, and so we're going to multiply by the conjugate. Here's how we do that. They didn't say the conjugate in the denominator, wherever your radical is. So the conjugate here for the numerator would be the square root of x minus 1 minus 2. And you're going to multiply the top and bottom by the same value. Let's do the math. We have the limit as x is approaching 5. When you multiply these two things, well, that's just going to equal x minus 1. And then when you multiply this over here, you're going to get negative 2 times radical x minus 1. Then when you do this math over here, that is going to give you a positive 2 radical x minus 1. And this over here gives us a negative 4. For the denominator, well, the denominator, I'm just going to leave it as x minus 5 times this. All right, I'm not going to get involved with that. You'll see why in a minute. Let's continue. These two cancel. Whenever you multiply conjugates, the middle terms are always going to cancel. Just think about this, right? If I were to multiply x minus 2 times x plus 2, what happens, right? You're going to get x squared minus 4. The middle term cancels. Same thing over here. When you combine these like terms, so now I have this is a negative 1, these two things canceled, and a negative 4, so I'm left with x minus 5 in the numerator, and the bottom is, oh, that's convenient. Look what we have. We can cancel out a common factor. Those cancel, and we're left with this. Now we can evaluate. Remember, evaluating is when you can drop the limit sign. We have 1 over the square root. We plug in the 5. And that's going to equal the square root of 4 minus 2, which is, that's 0. It looks like this is approaching infinity. And if it's approaching infinity, the limit does not exist. So that's going to pop up sometimes where you have an infinity, and there's an example of when. Let's do one more just like that, another conjugate. Okay, let me clean up some of our mess here. Here we go. Okay, now, I didn't mention before, but you always should, take a chance, because sometimes when you just plug it right in, it will work. So, but in this case, again, what we would have is we would get a 1 minus a 1. We'd have 0 over 0. So anytime you get 0 over 0, it's time to do something. Okay, let's do something. Let's multiply by the conjugate. And we have the limit as x goes to 0. And we're going to do the same thing. We're going to multiply, and that's going to give us x plus 1. These two middle terms cancel again. You can see that. And then the last term right here, negative 1 times 1, is negative 1. The denominator, just like before, we're not going to multiply it out. Just leave it. You'll see what happens in a minute. Let's combine all of our like terms. This right here is going to equal 0. So what we're left with, oh, look at that. If you're left with just an x in the numerator, well, we have a common factor. So what we can do here is we can cancel this common factor with this common factor. And what we're left with is 1 over this. Now we can evaluate. Notice how we're not going to get a 0 over 0? Let's plug it in. Take your 0 and you plug it in, and you're going to get, hey, this just equals this. Now you have 1 over, well, 0 plus 1 is 1. And, well, the square root of 1 is 1, so it looks like the answer here is 1/2. Nice job. Yes, that is a complex fraction. A fraction within a fraction. What do we do here? Well, we're not going to multiply by the conjugate. When you have a fraction within a fraction, here's my suggestion. The next plan of attack is we are going to simplify our complex fraction. And that will usually get us out of any situation that we're going to come across in this class. Let's, and just to check again, if you were to go ahead and take the 0 and first plug it in, that's going to give you 1/5 minus 1/5. It's going to give you 0 over 0. 0 over 0, we do something. Here's what we do in this case. We have to figure out the common denominator. Now, if you look at these three terms, right? I have three denominators. I have an x plus 5, I have a 5, and I have a 1. What is the common denominator? All right? The common denominator, well, I need one of these simple factors, which it's just 1. You don't really need that. I need one of these simple factors, and I need one of these simple factors. So the lowest common denominator is going to be a 5 times an x plus 5. Don't make that 5x plus 25 because you're about to cancel those simple factors out. Here's what you're going to do next. You're going to multiply the top and the bottom by the same value. Now let me pause for a minute because here's what 99% of you want to do. You want to get a common denominator on these three fractions, but think ahead. If you get a common denominator here, here, and here, what you're left with now is three really nasty looking fractions within a fraction. You can do it that way, it's just a little bit more error prone. Here's another plan of attack. Rather than getting a common denominator, you multiply through by the common denominator, top and bottom. Why top and bottom? Well, anything over itself is 1, and you're allowed to multiply by 1 without changing the value. So what happens in essence when you're doing that is, well, here when you distribute, you're going to distribute this here and here, right? So we're going to have something that looks like this. I distribute, and I have a 5 times an x plus 5 to multiply over here. I have a 5 times an x plus 5 to multiply over here. And of course on the bottom, we also are going to have a 5 times an x plus 5 to multiply. On this one, now I'm going to just put all these over 1 just to show you, because we're multiplying fractions. I want to make sure you see what cancels. Over here, I have an x plus 5 in the numerator and an x plus 5 in the denominator, and those two cancel. But when you do that, you're left with a 5 times 1 in the numerator and a 1 times 1 in the denominator. Well, 1 over 5 over 1, 5 over 1 is just 5. Now let's go and do this one. So here we can cancel out a 5 in the numerator and a 5 in the denominator, and what we're left with is negative, well, 1 times x plus 5 is x plus 5, all over 1. And the bottom, we're going to do the same thing. I can multiply the 5 and the x, but I'm not going to multiply everything out. I'm just going to leave it as this because something's going to happen. Now let's go up here. We have the limit as x is approaching 0. When you simplify this, this becomes negative x, negative 5. 5 minus 5 goes away. I'm left with a negative x. Upstairs is negative x. Downstairs is 5x times this. Notice we have a common factor. I can cancel out an x with an x, and now I'm left with this. The limit as x is going to 0, I have negative 1 over 5 times x plus 5. We get to evaluate now because there's no way we're going to get a 0 over 0. You plug it in, you're going to get negative 1 over 5 times 0 plus 5. This equals negative 1 over 25. In summary here, so a plan of attack for evaluating limits analytically. So the first thing you're going to do is you're going to plug it in, direct substitution. If you plug in the x and get an answer, great, you're done. But if you do that and you get yourself what's called indeterminate form, which is a 0 over 0, you must do something else. The next plan of attack, factor. Sometimes you'll factor the problem out, simple factoring or synthetically or long division. If there's a radical in there, you might want to multiply by the conjugate, rationalize that thing, top and bottom you multiply by. And if you have a complex fraction, simplify it. You'll usually get out of your problem. So now with all of these plans of attack, you have enough information to do this. You can finish homework 2 here and move on to day 2. Page 68. Page 68 has a bunch of evens as well. So what I did for you here is I left you page 68 with the answers right here. All right, so please note the answers are in blue and you do not have to rationalize your denominators. So whether you leave it like this or like this, you'll get full credit. Have a great day.